Okay, I think it's recording now.
All right, so hello everybody. Welcome to this MSc seminar by Ron Benchetrit. So a brief intro about Ron. So Ron graduated in BC in the Technion, the Science Department in 2022. And he's been pursuing his master's degree in the same department, the Science at the Technion since 2022. Okay, go ahead, Ron.
Okay, thank you, Vadim. So today I'm going to introduce our research titled Anytime Incremental rPOMDP Planning in Continuous Spaces. The talk is going to be in English, but feel free to ask questions in Hebrew as well. Okay, so let's start. Sorry. Okay, so we'll start with a small introduction. Then we move on to the mathematical background we need. Specifically, we're going to introduce the mathematical models, MDPs, POMDPs, and rPOMDPs. Then we talk about how we actually solve POMDPs in the first place and some current state-of-the-art approaches. Then we introduce our approaches, the challenges we faced, and the solution we found. And last, we'll conclude. Okay, sorry. Why this? Okay, so autonomous agents appear in a wide range of domains. For example, it can be autonomous driving, or it could be home assistance robots, and many more. And these agents must perceive the world through noisy and/or partial observations. They must act under uncertainty, and they must plan in order to achieve these long-term goals. This talk will focus on sequential decision making under uncertainty. Sorry, I think I hear uh, somebody can mute there. I'm hearing myself. Okay, thank you. And okay, so they must plan in order to achieve these long-term goals. And in this talk, we'll focus on sequential decision making under uncertainty. Specifically, we'll talk about planning in POMDPs and their extension, the rPOMDPs. Okay, so we begin by introducing MDPs, which are we'll begin by introducing MDPs, and we'll begin with a small example, because it will be easier to understand that way. So imagine you have a Roomba-like robot operating in this room, and its goal is to navigate to this designated goal area. And the robot acts in the environment by actuating its motors. For example, it can move forward, it can rotate left, it can rotate right. However, due to motor errors, slippage in the floor, and some other factors, the outcome of an action may not be as expected. For example, we might want to move a meter forward, but we might drift a bit to the left, drift a bit to the right, or in the range. And we want the robot to reach the goal as quickly as possible while also maintaining safety and not colliding with obstacles along the way. So now to the formal definition. A Markov decision process is defined by the tuple S, A, T, and R. S is the state space. For example, it can be all the robot positions and headings in the room. A is the action space. It can be, for example, move forward, turn left, turn right, or even a more refined turn left by 2 degrees, move forward by 20 centimeters, and so on. T is the transition model, and it basically is the conditional probability of reaching state S tag, given we were at state S and we performed action A. And a simple example can be just a linear Gaussian model that accounts for motor noise and slippage. R is the reward function. It's typically a function of the state and action. And just an example, we might have a big reward for successfully reaching the goal, a big penalty for hitting an obstacle, and a small penalty for each time step in order to encourage the agent to act quickly. And the objective in the MDPs is to maximize the expected cumulative reward. as kind of shown over the first formula. Y expectation because the dynamics are uncertain. If they were deterministic, we could drop the expectation. And a solution for an MDP is a policy that maps from states to action. And we can also define the value function, which basically describes what is the expected cumulative reward if we start from state S and follow policy pi. By following policy pi, I mean the actions are dictated by this policy. Similarly, we can define the action value function, which is notated by the Q function, which is very resembling of the value function. The main difference is that over the first step, we follow action A, and only then we follow the policy pi. And this gives us a nice recursive formulation with the value function. Okay, sorry. Okay, so we discussed about MDPs, and in the MDP setting, the robot always knew its exact location. And now let's assume that the position is unknown. We only have some rough initial guess. And the robot is equipped with sensors, for example, a laser rangefinder to measure distances to walls. However, these measurements are noisy and ambiguous, and multiple locations can produce similar readings. And in order to navigate effectively, the robot must estimate its position using both its action and sensors data. And now more formally, POMDP is a partially observable Markov decision process extends an MDP to handle partial observability, and it is defined by the tuple SATR, which are the same as in MDP, the state space, the action space, the transition model, the reward function. What is new is O, Z, and B0. O is the observation space. For example, it can be all the possible laser rangefinder readings that the robot can receive. Z is the observation model. And it is a conditional probability that tells us how likely it is observing observation O, given we were in state S. And just a small example, for example, a Gaussian distribution centered around the true distance to the nearest wall. Just an example. And B0 is the initial belief. A belief is a distribution over the states. In our example, maybe our best guess is just a uniform distribution over the room, meaning the robot has no clue where it is. So what is this belief? Let's introduce it more formally. In the MDPs, the agent can choose actions based on its fully observable state. In POMDPs, however, the state is hidden. So the agent must act based on what it knows so far. To handle this, the agent maintains a belief denoted by BT, which is a probability distribution over possible states at time t. And the belief is updated over time using the agent history of actions on observation, which is denoted by HT. And the belief at time t is defined as the conditional probability over the state given the entire history up to this point. Okay? And the objective in POMDP is pretty much the same. We also want to maximize the expected cumulative reward. But the difference now is that the policy maps from beliefs to actions, since we do not know what the actual state is. And the value function is defined also pretty similar to the MDP, where the main difference is it now a function of the belief, and that the policy is belief dependent. Other than that, it's pretty much the same. Similarly, we can define the Q function, which again is the value given we first perform action A and then follow policy pi. And it's also given by a recursive formulation. BTAG is the updated belief after we perform action A and observe observation O. So how do we actually update the belief? Typically using something called the base filter. So this is a general formulation for the base filter. And let's look at the terms. The first term, Z, is how likely is that we actually see the latest observation given we were at state ST. And the second term is how likely it is we got to state ST in the first place. And eta is just a normalization constant, so this will be a value distribution and will sum to 1. Some special cases of the base filter include the Kalman filter, which is suitable for linear Gaussian systems, and the particle filter, which is more general and can be applied for nonlinear and non-Gaussian systems. So let's dive a bit more deeply to particle filters. So particle filters approximate the belief using a set of weighted samples, which we call particles. Each particle represents a possible state and has an associated weight. So for example, let's look on the right. We can approximate this density using these weighted samples. And you can see that where the density is larger, we have a bigger weight. And this representation is very flexible and is well suited for capturing complex or multimodal beliefs. And as the number of particles increases, the approximations becomes more accurate, and we will use this property later in our approach. But how do we actually update the particle filter? This is more of a bonus. So if you don't follow this slide, it's okay. Say we have some particle approximation at time t minus 1, which is represented by a set of weighted samples. So the first thing we're going to do is called resampling, where we resample from this particle according to this weight. And what will happen is that particles with bigger weights might receive multiple copies, but particle with very small weights might be neglected. It's actually very important for the stability of the particle filter. The step after that is called a prediction step, where we propagate each particle using the transition model. We basically sample a new state given the state of the previous particle and the action. And we do this for all the particles. And the last step is the update step, where we assign each particle its weight according to the observation model. Okay, so we talked about MDPs, POMDPs, beliefs, and particle filters. Now let's move on to rPOMDP. And as before, we will begin by an example. So earlier we wanted the robot to reach a specific goal area. But now let's suppose that its task is to localize itself in the room. There is no designated goal location anymore. The objective is to just reduce uncertainty about the position. And some examples for this kind of problem can include active localization, like we just described, informative path planning, active learning, and active SLAM. And this task cannot be naturally expressed using the standard state-dependent reward. Since, again, we don't have really a designated goal area, the robot can travel where it wants as long as it reduces uncertainty about its position. What we can do instead is define a belief-dependent reward function, which is now a function directly over the belief, which just a short reminder, belief is the distribution over the state. And just an example over that can be a negative entropy. And now more formally, rPOMDP is pretty much the same as POMDPs. And the main difference is that we replace the state-dependent reward R with a belief-dependent reward ρ. Okay, so ρ is dependent on the belief and maybe also the action. And some examples can include mostly information theoretic rewards such as entropy or information gain, mutual information, and so on. And this formation naturally captures tasks centered on active information gathering. Sorry. In practice, RAW can combine both belief-dependent components and state-dependent components. For example, if we go back to our problem with the Roomba robot, we want it to localize, but we also don't want it to collide with obstacles. And the objective in rPOMDP is again to maximize expected cumulative rewards, only that this time the rewards are belief dependent. But the policy is still the same, it's still a mapping from the belief space to actions. Okay, so we introduced the mathematical models we use to model our problems. We introduced the MDPs, POMDPs, and rPOMDPs. Now let's talk about how we can actually solve these problems, how we can solve POMDPs. So solving POMDPs is very hard in general, and finding an exact solution is impossible for all problems, but very small naive problems. And this is due to the following reasons. The first is the curse of dimensionality. If we take the state space, for example, it grows exponentially with the dimensions. And this makes representing beliefs exponentially harder as the dimensions grow, whether it's an explicit representation or whether it's a particle-based representation like we discussed before. The second problem is the curse of history. The number of possible histories grows exponentially with the depth, with the number of steps in the history. And therefore, the amount of possible beliefs in our space also grows exponentially. And these problems becomes even harder when we're dealing with continuous state, action, or observation spaces, which are the focus of this work. Okay, sorry. Okay, so in general, we can define POMDP solvers into two categories. The first one are offline methods, and the second is online methods. In offline methods, we aim to compute a policy that maps from beliefs to action in advance. So we compute it in advance, and then we can just deploy our agent or robot in the true environment. However, this requires solving for the entire belief space, and it's computationally intractable for large or continuous domains. Some examples include value iteration or point-based value iterations. However, today the main focus is on online methods. Online methods interleave planning and execution, and at each time step, they compute the next action based on the current belief. Then we perform the action, receive an observation from the environment, update the belief, and the cycle repeats. And the benefits of this is that we avoid planning for unreachable beliefs. We only focus on what's reachable in the next few steps. And therefore, it's much more scalable in high dimensional or continuous settings. And some popular examples include POMCP, Despot, and POMCPOW. So online methods typically plan using a tree search. And they build this tree search rooted at the current belief. And this tree is called the belief tree. And nodes along this tree represent beliefs, and edges correspond to actions and observation. So, for example, the root is B0, maybe our initial belief. And if we take a few steps down and select some node, it's a belief that is conditioned along the actions and observations along the path to that node. And the tree is expanded by simulating action and observation trajectory. And once we finish with the search, the best action is selected based on the estimates at the root. And then we perform that action and the cycle repeats. However, note that constructing the full belief, given all the actions and all the possible observation, is intractable. Okay, it's because we said the curse of history, the number of possible histories or belief grows exponentially with that. I should also mention that maybe our objective is to solve the infinite horizon problems, but the search tree approximates it using a finite depth, which is a parameter that the user must choose. The larger the depth, maybe the approximation will be better, but it will be much more computationally expensive. Okay, so let's move on to multi-colored research. Multi-colored research is a very popular planning algorithm, both in POMDPs and games, chess, Go, and more. And it uses random trajectory simulations to estimate values. And MCTS builds the tree incrementally using 4 key steps. The first step is selection. We select a child node based on a selection strategy, for example, UCT, until an if node is reached. Then we expand that node, we add one or more child nodes, and we, in the simulation phase, we simulate a rollout from the new node to estimate its value. And a rollout is just a random simulation. Typically, we guide this simulation with a rollout policy, which can be maybe a completely random policy, choose action at random, or it may be something more sophisticated using some domain knowledge. And in the backpropagation step, we propagate the return up the tree and update value statistics along the path. Okay, so most state-of-the-art online POMDP solver rely on some sort of MCTS. And most of them use a particle-based approach to represent the belief, either explicitly or implicitly. This is due to the facts we said earlier that the particle filter is very flexible and it allows to represent a complex and multimodal belief. And we can broadly categorize these solvers into 2 categories. The first one is state simulators, and the second one are belief simulators. So state simulators simulate state trajectories directly. And as we can see on the right, the red particles are new ones that added along the most recent simulation. So each time a belief node is visited, we add a new particle to that node, and particles accumulate across a visit. And this is helpful because the representation will improve at frequently visited nodes. And because of the way MCTS works, these are likely also the promising ones. So the byproduct we get is that where we found interesting regions in the belief space, we also have a better representation, which is a very good property. The downside is, however, that computing belief-dependent rewards is much more challenging in this setting, and we'll talk about it more later. Some examples include POMCP, POMCPOW, Despot, LabCot, but there are many more. In general, I think this is the more popular approach to solving POMDPs. Belief simulators are a bit different. They treat belief states as explicit nodes in a belief MDP. A belief MDP is just an MDP where the states are beliefs. And each belief is represented using a fixed set of particles created once upon expansion. So if we look at the right, in the last simulation, we only added a new node with a new set of particles, but we didn't alter the belief nodes along the path. And this representation is static, and it might be a bit wasteful. For example, if we have a region in the belief space that is not very promising, we still need to allocate a good amount of particles to search there. And this example, there are just 5 particles, but in real problems, we need many more. And on the other hand, if we do find a region that is promising, maybe we want to improve the representation over there. However, we can't because the representation is static. The benefit is that computing belief-dependent rewards, for example, entropy, is really easy in this case because the belief is static, and we only need to compute this reward for each belief once upon creation, and that's it. Some popular examples are PFT-DPW and ADOPS. Okay, so let's look at raw POMDP solvers. Okay, so far we talked about POMDP solvers. Let's look at raw POMDP solver. And we can see that in the continuous setting, where we have a continuous state space, action space, or observation space, we can see a lot of solvers that use belief simulations. However, there is no solver that uses state simulations. And this is where our contribution comes into play. We introduce rPOMDP, and the goal is to extend POMDP, which is a state-of-the-art state simulator for POMDPs, to the raw POMDP setting. And we are interested in state simulators because they allow us to dynamically represent the belief and have a more refined representation. However, this extension has several key challenges. The first one is value estimation. The running averages using POMDP are incompatible with belief-dependent rewards. Belief representation, the particle accumulation during visit does not ensure sufficient belief quality across the tree. And lastly, and most importantly, reward recomputation. Belief updates require frequent and costly reevaluation of the reward function. And in the next slide, we'll address each of these challenges in turn. Okay, so the first challenge is value estimation. So in POMDP, nodes values are estimated using running averages of sampled rewards. Okay, so if you look over this approximates an expectation, and capital RI is just the cumulative return we received from the I simulation starting from this node. And this is well suited for state-based reward, where the expected reward depends only on the state, and we just need to average over different rewards. In raw POMDPs, however, rewards are non-linear function of the belief, and the belief evolve as new particles are added. And averaging rewards across outdated beliefs will lead to a biased and inconsistent value estimate. And we only want to use the latest reward since it is computed on the most updated belief, and it will probably be the most accurate. So the solution we use for this problem is adopting the less value update approach, which was already proposed in an earlier work. And in the LVU, less value update, each node stores a value estimate based on only on the most recent rewards. So we don't mix outdated rewards in this setting. However, the standard LVU formulation requires summing over all the children each time we update, each time we do a simulation. And this takes linear time in the number of children, and this can be very costly in a large tree, especially in the continuous domains where the tree will keep expanding over time. We propose an incremental update that maintains the same correctness, but with just O of 1 computation. So the formulas get a bit messy, but you can see the full deviation in the paper. Okay. Sorry. The second problem is belief representation. Beliefs are typically represented using a particle-based approximation, as we said before. And in state simulators, particles are added incrementally during the node visitation. And this is really nice because it improves belief representation at frequently visited nodes, which is what we are interested in. However, less visited nodes may remain very poorly represented. And for belief depends reward, we need a good belief quality throughout the tree, not just locally, so we can evaluate rewards in a good manner. And the solution we found, we call it anytime belief refinement. And we ensure that the belief quality improves over time and throughout the tree, not just locally. Our approach provides theoretical guarantees. Under consistent selection strategies, every node is visited increasingly often. And this enables belief refinement even in deep or rarely explored part of the tree. And further details and formal results are available in the paper. And the last challenge, probably the most important one, is the reward recomputation. In rPOMDPs, rewards depends on the belief, not just the state. And as the belief evolves, for example, when new particles are added, the reward must be updated accordingly. We only want to use the latest belief because it is the most accurate one. However, belief depends rewards are often non-linear, for example, entropy, making these updates non-trivial. On the other hand, they're very expensive, and they're very expensive to recompute from scratch each time. And this will become a very big bottleneck, especially in continuous domains, because in the continuous domain, the particle representation might grow unbounded. So we want a way to update rewards incrementally without full recomputation from scratch each time. And we will focus on information theoretic rewards, specifically entropy, because these are the most common rewards in raw POMDP. However, this approach is general and it can be applied to other rewards as well. So the first reward we will look at is the Shannon entropy. Shannon entropy is a very common information theoretic reward used to capture belief uncertainty. And if we look at the Shannon entropy over particle filters, it looks like this. However, recomputing this reward after every belief update is linear in the number of particles, which might be expensive as the number of particles grow. We factorize this term and derive an equivalent form that enables fast and incremental update. And this formulation allows us to update the entropy in just O of 1 time, each time the belief is updated by caching some terms. And you can see the full derivation in the paper. And the second reward we look at is the Bohr's entropy estimator. So the Shannon entropy is very simple, but it's not suited for particle-based belief, since it fails to capture local densities in the particle. And this is a trouble, especially in continuous spaces. And the Bohr's estimator, however, is specifically designed for such settings, and it manages to capture local densities and the overall shape of the belief. And it is defined by this complicated equation. But what's important for us is the last term, which is a nested sum over the particles. And this is the computation bottleneck. It takes of n squared time just to compute this term. We will show now that this term can be updated incrementally and efficiently. Okay, so recall the last term, which was expensive to compute. And let's denote this inner term this inner loop Ci. Adding a new particle number n+1, will affect all Ci for all I. However, we can incrementally update them like this, very simply in just O of 1. And all that is left is compute the last column for the new particle. Therefore, the total cost drops from O of n squared to O of n, and we get the same exact result. And this is a major saving in computation. Okay, so we talked about the problem we faced and how we approach them. So now our algorithm is ready, and let's talk about the experiments. So we implemented rPOMDP in Julia, which is a high performance language, using the POMDPs.jl framework. And the source code will be available soon at this link. We compared our algorithm against state-of-the-art solvers on two benchmark domains. The first one is continuous 2D LiDAR, and the second one is active localization. We also wanted to evaluate the benefit of incremental reward computation. How much do we actually save in time and computation? So let's begin with the benchmark domains. So both domains share a similar structure. They're both set in a 2D continuous environment. We have a certain belief over the uncertain initial belief over the agent's pose. There are beacons scattered in the environment that provide noisy observations for the agent. However, they do get more accurate as the agents get closer to the beacon. We have overall 8 possible movement actions along the unit circle. However, the dynamics are stochastic, so we don't know the outcome is not known, is not deterministic. We also have a stay action that terminates the episode. And in the light dark problem, the task is to navigate to a goal region, like we saw in the examples earlier in the slides. The challenge in this domain is that the rewards are very sparse. We get a very large rewards if the agent succeed. We get a very large reward if the agent fails to reach the goal region. But in between, we might not get a significant reward. And information gain, which is in information theoretic reward, is used as a reward shaping to encourage localization. In the active localization task, the task is to just localize in the environment. Therefore, we want to reduce uncertainty about the position. And in this problem, the reward is pure information gain. There is no goal area to go for. However, the environment includes obstacles to make things more difficult, and we penalize upon collision. All results that are reported are averaged over 1,000 simulations with different seeds, and we report the mean return and the standard error. Okay, so for the first problem, the continuous 2D LiDAR, we can see that rPOMDP effectively outperforms all other state-of-the-art work, likely due to its effective and dynamic belief representation. And we can also see that despite the added cost of computing information gain, it outperforms POMDP. Okay, so meaning that the information gain helped in this problem, even though it had much more computational cost. In the active localization problem, by the way, I forgot to say, these are planning budgets for each time step. These algorithms are anytime, meaning you can give them any time budget you want. And as you give the algorithm more time, the result will probably be better. So we look at different budgets and report different results. For the active localization problem, we can see that first P50 DPW outperforms rPOMDP, probably because it has a better initialization for the beliefs, which helped in this very small time budget. However, as we increase the time budgets, we can see that rPOMDP steadily improves and outperforms the rest. Thanks to its anytime refinement of belief. As we give it more time to plan, the representation will be better, unlike the other, where the representation remains static and fixed and will not improve. Okay, and this is just some example trajectories for the active localization task. And the red one is ours, the rPOMDP algorithm. We can see that it managed to reach the farthest beacon and successfully localize without colliding with any obstacles. Okay, so we compared our algorithm against state-of-the-art solvers. Now let's look at the effect of the incremental reward computation, which was a major challenge in this algorithm. So we compare rPOMDP with and without incremental reward updates on the light-dark domain. And both variants will use the same exact random seed to ensure that they will expand the same identical search tree. And we measure each time we give the algorithm a number of iterations to perform, and we measure the time it took. And we can see that if we give it a pretty big budget, 10,000 iteration, which is actually pretty realistic in online planning, it's not an exaggerated number, we can see that computing the reward from scratch each time takes over 80 seconds, which is not applicable in real time at all. On the other hand, our approach using incremental reward computation remains pretty much linear in the number of iterations, and it can compute 10,000 iterations under about 1 second, which is much better. And this emphasizes that this is a very critical contribution for this algorithm to actually work. So let's conclude. We introduced rPOMDP, which is an anytime online research algorithm for solving rPOMDPs in continuous spaces. And our contributions include incremental LVU for accurate and efficient value estimation, anytime belief refinement with theoretical guarantees on belief improvement, incremental reward computation, enabling scalable use of belief-dependent rewards, and that the empirical results demonstrate improved solution quality and planning efficiency over other state-of-the-art methods. And in terms of limitations and future work, the convergence of the algorithm still remain an open question. And belief-dependent rewards, even with incremental updates, are still expensive to compute. And these are venues for future work. And that's it. Thank you very much for listening. And I'll be happy to answer questions if there are any.
Thank you, Ron. Any questions for the audience? Going once, going twice. Okay.
Okay.
No questions. Okay. Thank you so much, Ron.
Thank you, everyone. Thank you for listening.
Thank you.
Thank
Bye
you.
now.